approaches to CFT, and now we're going to see another one, which is a probabilistic construction of the CFT.
Thank you very much for the invitation. My talk will be about the probabilistic construction of the Liouville CFT. So it's a slow motion flashback of Guillaume's first two slides, maybe. So it's a joint work with many people. Here, so there is Guillaume here, Colin here, that will give a talk on Friday about the more precise talk about the conformal bootstrap that I will talk a little bit at the end of my talk. So basically, I want to explain the first part, this probabilistic construction, and then what I would try to do is to explain how to get the bootstrap formula from this probabilistic setup. I mean, in a pedagogical way, skipping perhaps some technical details. Get the idea. So, there are many experts of Liouville theory in the room. There are many people before us and after us. So don't hesitate to complement my talk with insights, remarks, whatever you want. But it's C bigger than 25. So
Maybe it's a bit too, I think it's not that problem. It's just that you need to minimize it a little. Okay, so to start with, in the physics books, you see that the Liouville theory, more or less, it's a path integral. So here, you can think of it as a functional, as a measure on a functional space. Your integration variable phi lives in some functional space. This is what it means. And basically, here you have to think of it as the uniform measure on the space of all possible maps defined on some Riemann surface, equal to the metric G. And so here F is just some observable that you want to test with your measure. You want to weight this uniform measure on maps by this Liouville action, which is this expression here. So inside you have here, this, just to set my notation, this is the volume form on the manifold. Here you have the Ricci scalar, and here this is just the gradient of the map. Okay, so there are a few parameters in this expression. The main one is this gamma, which will be between 0 and 2. The Q is fixed by gamma by this relation, and the mu is just a scale parameter, but actually the theory is invariant with respect to the mu. So it's not a real parameter of the theory. So there is only one parameter, which is gamma. And in the end, it would give me a central charge which is bigger than 25. And what you want to do is formally you want to compute the Laplace exponents of this field, which are this vertex, they are called vertex insertions. So you want to plug these operators in this measure here and evaluate these quantities, where you take arbitrary points, x1, xn on your manifold. And your Laplace exponents, they are just real numbers with some constraints that I will discuss later. But okay, and if you want to ask, yes, you can take some complex values also. But for the probabilistic expression, to start with, it will be alpha real. Okay, so questions so far? Okay, so this is what I want to. So I want to explain that this is a conformal field theory, and there are many ways to define in math what is a conformal field theory. And each definition is already an EV, it's an EV stuff. And furthermore, checking that one model that you have fits this definition is quite work. So I will just focus on the Segal axioms. The reason is that first, it's a geometric description of what is a CFT, but it is well fitted to probability theory, to bridge the gap with probability, and this is why we choose this approach. And I'm going to explain a little bit what is this approach by Segal. So, Segal approach of CFT is well, it's a correspondence. Correspondence means that you have it's a correspondence between two categories. So in the first category, you have circles and disjoint union of circles. So let me draw a picture to explain why you have this. So basically, you will consider Riemann surfaces with boundary. So something like this. The boundaries, they will be your the boundary components of your Riemann surface. And in between, you will have a Riemann surface. So there are colors in my pictures, because actually it's not written on my slide, but these boundaries, they are equipped with the parametrization of each boundary circle. Okay, and there are two cases. Either this parametrization has the same orientation as the orientation given by your manifold, in which case the boundary component is said out. So here you have out boundary components. And if the orientation given by the parametrization is inverse to that of the manifold, then, sorry, it's this, yes, inverse, you call it in. So you have these circles, this circle, the disjoint union of all the circles for all the boundary components, and then the morphism in your category is this Riemann surface in between the in and out boundary circles. Okay, and this correspondence is a map. So to a given circle, you will attach a Hilbert space. Okay? It's model dependent. Okay, so I will discuss a bit later what is the Hilbert space in my case. Then to the union of boundary circles, you will attach the tensor product of the Hilbert space. So this is the state of the space of states. And then to the Riemann surface in between, you will attach an operator. So in my talk, I will make the confusion between operator and integral kernel for an operator. So here, for now, this amplitudes, what are called amplitude, these operators, there will be elements in HB. Actually, it's not completely correct in this picture. Actually, the amplitude, it will be a map, an operator, from the tensor product of the Hilbert spaces attached to the components, mapping to the tensor product of the Hilbert space attached to the out.
Sorry for my complete ignorance, okay? So, when we do this correspondence, do we a priori fix the genus of the Riemann surface or not? Because in my, so in that picture, I could also not have the whole, right?
You define this correspondence for all the possible joint union and all possible Riemann surfaces in between.
Okay.
So you can take any genus if you want. You can still have this amplitude attached to any surface. Okay.
Does this map depends on the metric on the surface?
Yes. Okay. So yes, it depends on the metric.
Ah, so G is a metric, not G.
Yeah, it's a metric on the manifold. So the metric it has to be at the near the boundary. It has to be nice enough, meaning that you can. When you glue this surface, the glued metric defines a smooth metric on the whole manifold. So I will skip a little bit that part in my talk about the regularity of metrics. But okay, They have to be nice at the boundary. And of course, this correspondence, so there is these Riemann surfaces, they behave well when you glue them together.
Geometric, I guess. And genus is kind of hidden in sigma.
Okay, you can glue two Riemann surfaces along the boundary to get this one here. And this correspondence has the property that when you glue metric surfaces, this map, it maps to composition of operators. Okay, so it sends the gluing of surfaces to composition of amplitudes. This is something that I will explain in more details in a minute. Okay? Yes.
Alpha, are they collection of integer numbers or?
Are they what?
What is alpha?
What is alpha? So here, yes. So basically, so the x here. So just thanks for the question. I will use. So there are many notations in this stuff. So I will use the bold type for collective notation. So x is bold here. This means that I have a collection of points. So in the mini-poles, say this one, x1 here, x2, and x3. The bold x is the collection of all these guys. And these guys, they have a real weight attached to each of them. So alpha 1, alpha 2, alpha 3 for now. And this is bold alpha. And for now, you will just take this alpha in the real numbers, but this is specific to Liouville. Usually, you will index, alpha will serve to index the primary fields of your CFG.
Excuse me, just another question, sorry.
Because if you touch it with the finger, it kind of...
So metric-wise, do you have a statement about gluing those metrics on?
About the metrics.
Yeah, the metric on. I have a metric on the pair of pants. I have a metric on the torus with two holes, and now I create a metric on the.
The glued metric may be not smooth.
Okay.
Okay, so in local coordinates, here the metric near the boundary, it has to be, say, G is of the form dz squared over z squared, so that it's like a tube, and you can glue the tube together. Okay. So this is just to have a smooth metric on the glued manifold. But if you don't do so, you have some extra terms appearing. You can still handle non-smooth metric, but you have to be careful.
Yeah, this is when you view a polar neighborhood of the boundary to an annulus. No?
Yes, yes. So this is a tube.
It's a flat metric.
Yes.
This length of circle is 2 pi.
So yes, this metric, you can see it as making the collar here like a very flat tube. So that you can nicely glue with another completely flat.
So do you have twists or not?
When you glue, you can have twists, yes. And actually, you can, so in the boundary parametrization, so you have for each component, you have a parametrization. So this is a map from the unit circle to the boundary circle here. And it has an origin, which is mapped to somewhere here, let's say here. And when you will glue together the metric, the points have to match, so you have to twist a little bit.
You use the parametrization for gluing.
Yes, you use the parametrization, yes, for gluing. This is why you have to match the points. Okay, so so what I want to do now is to explain a little bit how this works with the Liouville theory.
Are the marked points only in the bulk, or are they allowed to be on the bulk?
Yes, I will take them in the bulk. This is not a boundary CFT here. I will deal with the bulk, but this amplitude, they will serve to decompose your bulk theory into pieces, and you better avoid having points on the boundary. Okay, so I will discuss in a minute how you construct the Hilbert space, the amplitude in the Liouville theory, but just I want to explain why you use this amplitude first. So the idea with this amplitude is that they represent your path integral, but conditioning the integration variable on some boundary fields. Okay, so this is this phi is a map from your manifold into R, and so you want to fix the boundary value of your integration variable. Okay, so basically this phi j here, they are functions defined on the boundary circles, and you want your big phi here to match these fields on the boundary. And so this is like a conditioning of a measure. Okay. And this amplitude, they represent your path integral with the insertion here corresponding to the marked points that you have inside. And you condition this integration on some prescribed boundary values. And basically, so since this phi j, they will be more or less function defined on the circle. Your Hilbert space, you expect it to be some space of maps defined on the circle. Okay?
And you don't have to include like boundary terms in the expression. Usually, when you have a boundary, we also include some boundary terms.
Yeah, the point is that it's not, I insist, it's not a theory on boundary. So here, this is just a tool, a way of seeing your path integral by cutting it into pieces. I will not deal, you can do the same picture, but it's more complicated for boundary CFT. But here I will only use all of this for bulk theory. Okay, so only in the end, only close the Riemann surfaces. Okay. I will, maybe the next slide will be a bit more. The point is that when it might be the case that your surface sigma is closed, so with no boundary, in which case your amplitude is exactly the correlation functions. Okay. Okay. So this is the intuition for this path integral. And why do you want to use this? Because they have a nice gluing property. So if you look at your path integral on the wall closed Riemann surface, and then you can cut your surface with a curve, a circle. And the point is that your action is local. This means that if you look at the Liouville action on the wall surface, it splits into the action on each part of the manifold. And so if you disintegrate your measure, here this is the path integral where you integrate over the whole manifold, you can disintegrate this measure with respect to integration along the circle. So it's just a condition on the values of the capital phi along this boundary, this circle here. And you can see that formally, at least, your path integral, you can write it this way. So you just integrate over the boundary field the path integral that you have on each part of the manifold, so here and here, conditioned on some prescribed boundary values. Okay, this means that you can cut this path integral on the wall surface into the gluing in the Hilbert space of these two pieces.
It's just form. I mean, you have to define what do you mean by define the measure. How do you integrate?
I have to define everything here. This is just a physics picture, if you want, the motivation. Okay. So this property here, it will play a role. This is what Segal had in mind when he designed this approach, because he wanted to. So what is it? How do you cut a surface in a nice way into a pair of pans? Okay. So you have, in the end of the day, you will have a big surface. You will cut it into a pair of pans. Then you use the Segal gluing axiom to say that I glue all these pans together, and these pans, I will relate them to the structure constants. Okay? So this is the picture Segal had in mind.
So sorry, that's what I am struggling to understand a little bit, because you're saying, so in this example, you're considering a compact genus 2 Riemann surface,
Yes.
and you're saying I need to compute some integral on it, so I split it in two parts. That's fine. And then you're kind of using Stokes' theorem on each part, right? But I don't see in the result I don't see the phase of the gluing, so I don't see the twist. And that must be something that comes to
the twist.
So when I split and then I want to glue back, I can glue back this way or twisting.
Yes,
And
but
this
I don't glue, I cut.
Yes, but then you cut and you compute something
Yes.
by cutting it.
Yes.
And I don't.
So there is no twist because here, when I cut, sorry, when I cut, the twist is fixed. I cannot play with the twist. It's just that if I twist, it's not the same surface.
Okay.
The curve is parametrized also. So
Okay.
you pick the parameterization. So
It's a sort of a geometrical representation of OPE.
Yes, exactly. Yeah, it's a geometry. Yeah, if you like.
It's a
Yes.
bit confusing because on the right hand side you have two metrics, G1 and G2. But
Yeah. Okay. Yes. So when you have a metric on the surface and the restriction to each part is
so
G1.
there's another condition like that they kind of glued inappropriately.
Yeah, the metric has to be on this form here in local coordinates. It has to be smooth when you cut.
And somehow this includes this twist. I mean, the way you glue them, twist just in the right hand side. as I do.
I can glue and cut without metric. I mean, it's a property of charts gluing.
Yeah, that's
So I can completely skip the metric
Yes, yes,
and still keep track of the twist just by. Okay, so this is this picture that more or less motivates Segal correspondence. Okay. So now let me describe a bit more precisely the Hilbert space. So as I said, you expect the Hilbert space to be some space of maps defined on the circle. So these maps, I will expand them in trigonometric series. Okay, this is a trigonometric series on the circle. I single out the zero mode because it will play a special role. And then I can parameterize all the Fourier coefficients under this form where I split the real part and imaginary part up to the square root of n parameterization. And you have a Sobolev space of maps, which is the space of all these trigonometric series satisfying this condition. And here the important point is that I would put a measure on this Sobolev space, which is this product measure. So in this series, C, the zero mode, it will be sampled according to the Lebesgue measure on the real line. So this is not a finite probability measure, but still makes sense. Okay, so this is a Lebesgue measure on C, and here each component xn and yn are just IIG Gaussian under this measure. Okay, so it's just a family of IIG Gaussian. So you can see this map as a random series if you like. These guys are Gaussian, and this one, this zero mode C, is sampled according to the Lebesgue measure. Okay, so your Hilbert space is just the L2 space.
Here you're summing coordinates.
What?
Here you're summing the coordinates, right? It's like there's an implicit sum of otherwise it's R times H minus S.
Summing the coordinates. I just put a measure on the Sobolev space.
Yeah, but you have DC times P, but you're summing coordinates implicitly.
In this type, you mean?
Yeah.
If you want.
Yeah, I'm just saying something trivial.
Okay, so basically, well, you have a, well, anyway, in the end, you have a space, a measure on this space. You can consider the L2 space on it, and this will give you your Hilbert space. Okay? And for probabilist, this decomposition here is just the law of the GFF on the circle. Okay, so this is my Hilbert space.
One question: is it theta from torus, or
is it what?
What is theta? The
Coordinate
coordinate
on the circle.
on the circle.
Yes, sorry, it's a coordinate on the circle. Yes.
I think this is what usually we call d phi, right? It's derivative for free field, no?
This is free field, you said?
I mean, usually in physics, the right-hand side is supposed to be for d phi, derivative of phi, no? Because, like in the previous lecture, C was multiplied by theta. Oh, am I saying wrong?
This is a gap.
Just a question. There is a...
No, I mean,
But maybe
for free field, which we know, like free field.
No, because
No, no, I
need to find
But then
bias.
C has to be multiplied by theta.
no, but it's not in the light cone. It's not a light cone here. That's just
Yeah, I see.
it's just a unit circle here that I identify with a 2 pi periodic function on the real line. No, I don't have. So there is only one circle here.
And can you say again what is xn and yn?
So any trigonometric series, I can expand it this way. Trigonometric series, a 2 pi periodic function, I can expand it this way.
Basically, you identify the negative Sobolev space with a series C phi n bar.
Okay, just I have a trigonometric series. I consider the space of all trigonometric series. That's arbitrary. Okay. Each coefficient phi n, I can parameterize the way I want. There are 10,000 ways of parameterizing the phi n, and my favorite one is this one. Okay. I could also just keep the phi n, but I could use 10,000 other parameterization, but I choose this one.
So we don't speak about any Riemann surface right now. So it's
Nothing subtly here. Okay. So just I wrote a phi n under this form. It's unique. And then I define a measure on the xn and yn, which is this Gaussian measure.
T is the circle, not a two-dimensional thing.
Yes, T is the circle. This T here, this is my circle. Okay. That's okay?
Yes.
So now the amplitude. So how do you define? So I have the Hilbert space. I have now to define the amplitude. So draw the picture. So you have basically you have a surface might look like this. So I can take any Riemann surface with boundary. I choose arbitrary points on the surface. Okay. To which point I attach weights, alpha 1 and phi n. And now I will impose that they are less than q. Okay, so the alpha j, they are less than q, and q is this real number that is related to gamma. Okay. We have gamma in 0,2, and q was to gamma.
So maybe the confusion that is that you use the x1, xn for the mark point, and you also used it for this phi n, so completely different things. So
Okay. Okay, so now
no, I got it's fine.
Okay, sorry. Thanks. Yes, so now I switch back to Riemann surfaces. I have mark points. I completely forgot the Hilbert space. So I want to define this amplitude I told you about, and you have this probabilistic definition, which is this one. So here I fix, so on each boundary circle, I attach some boundary fields. Okay, phi 3, phi 4, and the bold phi is just phi 1 up to phi 4. So it lives in the Sobolev space on the circle to the power of 4. Okay, so it's just a collection of 4 fields, 4 boundary conditions in the Sobolev space. And I want to define the path integral condition on these boundary values, and actually you have a way to understand this in terms of the Gaussian free field. And this is what I'm going to explain here. So here, expectation with the phi in index means that actually you just take expectation over the Dirichlet GFF that I'm going to explain in a minute. Here you see that you have the terms appearing in your Liouville action up to the gradient squared, but the gradient squared is hidden in this expectation with respect to the Dirichlet GFF. Okay. So this is exactly the path integral condition on the boundary values, but what keeps track of the expectation, the gradient square is this free field amplitude here, A0. So how do you define this quantity? So this A0, this is what you would get in the case of the GFF only, with no mu, with no potential. And this amplitude, so they have a mathematical definition. So here you have some geometric terms. So this is here just the determinant of the Laplacian. So you are on a manifold, you have a metric, you can define the Laplacian. And this Laplacian, you can define its determinant. You need to regularize, it's a subtle thing, but it's not that much important in my talk. Here, this is an operator. So it's D sigma is the GN map on the manifold. So GN map means that this is a Dirichlet to Neumann operator. Okay, so this is a geometric operator. You have some boundary. It's not important, just saying a word, but it's not important in my talk. You have boundary fields. You consider the harmonic extension inside the manifold of this boundary field, and then along the boundary you take the normal derivative, and this will give you the Dirichlet to Neumann operator. So this is just a geometric operator. Here, this is just the D here. You can think of it as the Dirichlet to Neumann operator, but on the disk. And this is a term that arises from computation because of my choice of the Hilbert space. Anyway, the point here is that this term, it's a geometric term that is completely explicit, and it comes from GFF computation. It won't be so much important in my talk. Well, what is important here is that what you've got in this expectation. So the big phi here, you can split it into two parts. Here, xj is the Dirichlet GFF on your manifold. So let me remind you what is this GFF. It's just the sum over all the eigenfunctions of the Laplacian on your manifold. No, not lambda alpha n, beta n. So these guys here are just IIG Gaussian, standard Gaussian. This En, the eigenfunction of Laplacian, and with eigenvalue eigenvalue lambda L, and you put Dirichlet boundary condition. Okay, so this is a function of x because you have some x here. The eigenfunction of Laplacian, they are defined on your manifold, but here you have some randomness. You can put it with omega if you like. So this is a random function of x. Okay.
With zero average and the zero mode, you put it in the field.
So there's no average because there is no condition of average because it's a Dirichlet GFF. And here, the p phi, this is the harmonic extension of the boundary field.
Yes, the zero, the constant.
Yes, it encodes the harmonic extension of the constants that you put on the boundaries. Okay, so there is no zero mode here, it's hidden in the p phi. Okay. So it's not, what's not completely straightforward in this expectation is the exponential gamma phi here, because actually the GFF, it's not a fairly defined function, it's a bit wild. Okay, so if you want to to exponentiate it, you have to work a bit. This was mostly done by Karen. Well, there is a whole theory called Gaussian multiplicative chaos for this exponential of the GFF. And for this, you have to regularize it a little bit. So the way you regularize it is not that much important because the limit that you will get is not regularization dependent. Okay? So for instance, you can take a modification at scale epsilon of your GFF. Then you want to define this measure. Here, this is just the volume form on your manifold, and you take as a density the exponential of the GFF. If you want to take this limit, you observe that it diverges. You have to tame a little bit. The right taming is this epsilon to some power. And this defines a random measure. It's a measure on the manifold, but it is random because of the GFF. So it defines a random measure on your manifold, and this limit is non-trivial, provided that gamma is not too big, which means gamma is between 0 and 2. Okay? So this gives you a random measure on your manifold, and then here you have the total mass of this measure. Divide the measure over the manifold. Okay, this is a random variable then, and it is finite almost surely, so that you can make sense of this term here. The term involving curvature is not too bad because recall that phi is basically a Gaussian field, and you take a linear perturbation, so it's not a complicated one here. You have a bit more trouble with this term here, because actually, as I said, the free field is not fairly defined function, so you cannot evaluate it at some given point. It's a distribution. But here you can regularize it again in this way, and there is a way to pass to the limit. Okay?
So the geometric term comes from the fact that in the boundary field you want your law to be P, right? Shouldn't it be like a ratio of determinants?
This one?
Yeah, doesn't it come from like a change of covariance in your...
Yes, the Hilbert space, in some way, I don't want to say this, not to dissolve, but in some way it's a bit arbitrary. So you can change it, but if you change it, you will affect the term here. You will change the change of Radon-Nikodym derivative.
But then is the determinant of the Laplacian just like the determinant of some ratio of D and D sigma, or?
No, here this is just the mass of the Gaussian measure that you get from the xj.
Ah, okay.
So it's the mass of your Gaussian integral. So this one, it's not related to the choice of the Hilbert space.
Okay.
Of course, okay, but not really related. And then here, this is what you said. Okay, so you have a probabilistic way to define this amplitude. Any other questions? Okay, so the theorem is that if your alpha j are not too big, meaning less than q, okay, and if the sum of the alpha j is bigger than some constant here, you have the Euler characteristic of your surface times q, then the amplitude, they do belong to the tensor product of the Hilbert space. The reason why you have this condition here is that what makes this guy here is well defined is the Gersonov transform. So it's in physics it's called the complete square trick. Okay, so anyway, you can remove this guy up to shifting the phi here. You shift it by a log of some power up to some multiplicative constant. So it creates in the measure a singularity. And the singularity, it has to be not too bad, and the too bad means alpha j less than q. And this is some kind of Gauss-Bonnet theorem. Okay, there are some stuff to be made precise here, but under this condition, you have a well-defined probabilistic amplitude.
I'm confused. Could you explain a bit what is this parameter S doing for you? Why is it important?
Which parameter?
S was introduced on the previous slide.
It's the regularity of your...
Right, here, the S, the Sobolev space, this one here, it's not important. It has just to be negative, because it's important because you want, in your Hilbert space, the only constraints you have is that you want, where is the measure? Okay, so this measure here, the mu0 that you've got on your Hilbert space, you want it to be supported on this space. You want it to give a non-trivial mass to this space. And for this, you need the S to be negative, but it's true whatever the value. Yes, positive, but minus S negative. This is the only constraint, and the S does not matter so much.
So if you reduce the mu0 measure to the smaller space L2 of T, then this gives you 0 in some sense?
Yes, I would say. Actually,
maybe it's not well defined quite.
Yes, the measure mu0, it gives full mass. It is fully supported on these spaces here, but not on L2. So it will be ill-defined on L2.
And do the weights alpha need to be positive or not?
For now, my weights, I take them real, and less than Q. So Q is a positive value, so they can be, they have to be less than Q, meaning they can be negative. And for now, the probabilistic description, it uses only real weights. But after a while, maybe I can explain why you can extend it to any complex values. Okay, so this amplitude, they obey some rules. So the first rule they obey is that they are invariant under diffeomorphism. So this means that if you consider diffeomorphism on sigma, then the amplitude, they are invariant under default. This is the image of your manifold. This is the push of your metric. And all the points that you've got here are mapped by phi. And the weight doesn't move. Another property that you have is what you, Guillaume, asked this morning. This is the Veil covariance. So what if you change the metric by a scale? Local scale. So you multiply the metric by exponential of omega, where omega is a smooth function. Then the amplitude, they move in a completely explicit way. So you can remove the exponential of omega up to some totally explicit term. So here you have a global term, which is well, it's called the Liouville functional, actually. It's not the same as in the beginning, but it's also called the Liouville functional. Up to some parameter here, which is called the central charge, and in my talk it's 1 plus 6q squared. And here you have this product of the conformal factor evaluated at those points here. 3, these points here. And in front of them you have some special values that are called conformal weights. And in my case, they are given by this quantity here. So it's a polynomial of degree 2 in algebra. And so this is the local scale invariance of your amplitude. And this is how you start to see the central charge. Okay? So these are some geometric rules. So this is the same story for any CFT. What differs is the value of the central charge, the value of the conformal weights, but any CFT will satisfy these axioms.
So this omega vanishes on the boundary or not?
It has to be a little bit, yes, a little bit smooth on the boundary. You have to.
Also vanish.
It has to vanish, but not only you have the Neumann derivative to be nice enough. I cheated a little bit here. Yeah, okay. The best way of, simplest way of stating conditions on omega to make this statement fully correct is to say, let's take it, let's take omega to vanish over a neighborhood of the boundary.
Wait, sorry, you wrote that the conformal weight is complex now, so you're implicitly allowing alpha to be complex?
Yeah, okay, so what is not hard to see that when alpha is real, this one is real. So, but for later use, I take it complex. Other questions? Okay, so these are geometric rules, and the last one is this is the one I mentioned. So if you take two amplitudes, so there is a mass statement, but you have to understand it the way I tried to explain a little bit before, because I don't want to explain this in question. So you have two amplitudes, okay, with boundary components, two surfaces with boundary components, and I want to glue together these two boundary components to form a unique surface, which is this one. So if you glue, then the amplitude attached to each surface, they compose in this way. This means that you take this amplitude evaluated at some field phi, this amplitude evaluated at phi. This is why you have a trace. You take the same phi on each boundary component, and you integrate over the Hilbert space, like you would do for a Markov process. Okay, and then you get an object, and this object turns out to be the amplitude on the glued surface. Okay, so they behave very well under gluing. Okay, and these are the main properties that you want your amplitude to obey. Okay, and with this stuff, we will play some games now that are very nice because you can use pictures, and this is what I want to do now. I still have 15 minutes, right? Something like this. Okay, so now let me explain why the Segal axiom, they will describe the Hamiltonian and the spectrum of the theory. And this is more or less what you said, is a way of reformulating the OPE. But let me explain how you extract the OPE from this. Okay, so now the Hamiltonian. So I take an annulus, with the inner circle radius exponential minus t. So obviously, an annulus, you will grant me that it has two boundary components. Okay, so I can attach an amplitude to this annulus. The metric I take to be this one exactly. Okay, and I can define an operator acting on my Hilbert space, just seeing the amplitude as an integral kernel. Okay, so we have a probabilistic expression in terms of the GFF for this guy, but I don't want to give you too many formulas. So I will skip to this amplitude description. So here I have an operator. I have an amplitude. It has two boundary fields. I take one of them, and I act on function of on the Hilbert space. Okay. So this is an integral operator, so it turns out that this operator, this family of operators, because I can vary t, it's a contraction semigroup up to some explicit term which depend on central charge. So it's a self-adjoint semigroup, and it's also a contraction semigroup. And the idea is, if you ask why, the idea is more or less this one. What if you glue two annuli together? So the pink one and the gray one, say. You glue them together, I can glue them along the green boundary component, and in the end I still have an annulus. Okay? So they have a nice composition property. And from this actually you can prove that this is indeed a semigroup. Okay? So I wrote this semigroup under this form because there is an operator here, self-adjoint operator H, and this H, this generator of dilation, it's called the generator of dilation. It's the Hamiltonian of the Liouville theory. And now I'm going to have an explicit description of this Hamiltonian. Okay, this Hamiltonian, so we call...
So for a moment is the Hamiltonian of any CFT theory.
Yes, you can do this for any CFT theory, yes. The point is that depending on the CFT, H might not be self-adjoint, or so you may have some trouble with the H. Okay, so recall the parametrization in my Hilbert space. So I look at trigonometry series, and they are parameterized this way. Okay, so the H, we have a description. So how you get it? You just differentiate in time the expression, the probabilistic expression that you have, and you end up on this expression here. So here, this is a Laplacian in the C variable on the real line. Okay.
this is just a constant. The P here is the sum, which is here. So it's a sum of harmonic oscillators in the xn variable and yn variables. So it's a sum of independent harmonic oscillators. The star here just means a joint with respect to the Gaussian measure. Okay, so it's you have this sum of harmonic oscillators, and then here you have a potential, so it acts by multiplication. Okay, so you can think of it, this is what, more or less what Guillaume said yesterday, you can think of it as a Schrödinger type operator in field dimension. Here you have some kind of Laplacian, okay, and here you have the potential, the mu v. Okay? And this one acts by multiplication, and this one is the exponential of the free field on the circle that you integrate over the circle. So it's again, it's a Gaussian multiplicative chaos. You have to regularize this guy to define it. Okay, it's actually this potential is very bad actually, because if you look at GMC, actually in dimension. So because now we are on the circle, we call that. I have my circle T, and phi it's defined on T. Okay, it's a GFF on T on the circle. Turns out that now when you are in the circle, you are in dimension 1. Okay? And the condition for this random variable to exist is gamma less than square root of 2. Okay? So actually I work with gamma between 0 and 2. Okay? So this potential, depending on the values of gamma, it does not even make sense as a well-defined random variable. Okay? So you have to be careful with this guy. It's a bit, it's a wide potential. It's not very regular. But, well, this is the description we have. Okay, so now I will start to explain how you diagonalize this guy. What I want to do now is to get some DOPE, and for us, DOPE is the Plancherel formula. So I have some kind of operator. I want to diagonalize it, and then I will use this eigenstates as some Fourier coefficient to play with the Plancherel formula. Okay, so to begin with, to understand this operator, what I will do in the next part of my talk is to remove the potential, see how we can diagonalize this operator, make the Virasoro action appear in this setup, and then I will add the potential and give you a theorem. Okay, so let's look at the free field case. It's called the QGFF, so it's the same potential, the same operator, except that I remove the potential. Okay? So if you look at this operator, it's way more easy now because it's just a sum of, linearly independent operators. Okay, so you can just diagonalize this operator by making the product of eigenfunction of this guy and each of this guy. Okay, so this is what you can do. So for this guy, of course, the eigenfunction of the Laplacian are just these plane waves here. Then for each harmonic oscillator, you take the Hermite polynomial, but Hermite polynomial of degree kn in the variable xn. For each of this guy, you have this contribution here. Okay, you make the product of all these possible eigenfunction of corresponding operators. It's just that you require the kn, the sequences, the degrees that you take have to vanish at some point, starting from some range. Okay, so if you form all these products, you get a complete family of eigenstates for your operator. Okay. You can compute, so it's just a computation involving, for instance, annihilation and creation operators. You can compute the eigenvalues. They are given by these quantities here. So where do they come from? So the q squared is my q there. This q. P squared is coming from this p here. Actually, this is the argument to this guy. And then each Hermite polynomial will contribute to the nkn that you got in this.
Okay. So you have an explicit expression for the eigenvalues, for the eigenstates, and actually you have a spectral resolution, or Plancherel type formula, that you can expand the inner product in your Hilbert space against this spectral resolution. Okay, so now this is a nice spectral resolution, but this is not the one I want to use because it's not adapted to the symmetries of CFT. Okay, I want to change the basis, and instead of making the Heisenberg algebra act on these guys to create the eigenstates, I want to use the Virasoro generic. Okay, so to do this, let me again play with the Segal axiom. Okay, so now, just one thing, I will play with the Segal axiom, admitting that they are true for the GFF. Actually, just take mu equals 0, what I told you, and it gives you the Segal axiom for the QGFF, okay? So now, instead of taking annulus with two regular circles, I can take an annulus with a nice blue boundary, green one that is a bit distorted. And how do you define this FT? So you consider a flow of maps. So you take a vector field V, a homomorphic vector field on the unit disk. G is my unit disk. And I take it under this form. So it's just minus Z that you perturb a little bit by some power. And you look at the flow generated by this vector field. And actually, what it will happen is that this flow, it will shrink inside the circle. And so when epsilon is small enough, and it will give you a family of holomorphic maps defined on the unit disk, the FT. So FT is defined on the disk, and when you map the disk by FT, you get this white area here, and the boundary is this FT of the unit disk, the green line, okay? You still have an amplitude in the gray area, and you can still define an integral operator with this amplitude. Okay. It turns out that, again, you have a probabilistic description of these guys. It's a semigroup, and the generator of the semigroup, I call it H0 of V. So what it is, this H0 of V? So just one thing before I switch the slide, notice that when you just take epsilon equals 0, you can solve completely this stuff. You get that Ft is just a dilation by exponential minus t. And then the exponential, this H0 of V is just the Hamiltonian of the Q free field, the one I'm trying to diagonalize. Okay? So now, this will be my last slide for today, I think. So now, when you take epsilon non-zero, you get that your generator is the Hamiltonian of the free field plus some operators L0n and L tilde 0n. Well, actually, they are the two copies of Virasoro algebra, but you have a description of these operators L0n and L tilde. So it's called the Sugawara construction. So this is these operators, you can construct them with the Heisenberg algebra. So this means that you have some creation and annihilation operators, AN, for the first copy of the L0n, another one for the anti-holomorphic part. And then you expand this L0n in terms of these quantities here. So here the double dot means that you put the this is what, annihilation on the right? Is it creation or annihilation?
Annihilation on the right.
Annihilation on the right. So as soon as M is annihilation, so in my case it's a positive. Oh.
In fact, for n not equal to 0, it's not important because they commute.
When this guy, so it's just that you put. I forgot the convention. But, okay, but it's just that when one of them is negative, say, I think it's negative. You put it on the right. When the two of them are negative, it doesn't matter because they commute.
If n is not 0, they commute. All these commutes, so it doesn't matter that much.
Yeah, true. Okay, so you have a description of these operators. This is a construction. And you have these elements, they are what we call two representations of the Virasoro algebra. Anyway, this means that first, these two families, they commute. This is what's written here. This is a unitary representation, meaning that the adjoint of the L0n is L0 minus n. Same story for the child, and they obey the commutation relation of the Virasoro algebra. Okay, with the central charge given here. And your Hamiltonian, you can reconstruct it by observing that it's just the sum of the L0 at n equals 0 plus this one at n equals 0. And what I will do after this, not now, is that I will explain how you can diagonalize H0 using these operators. And then I will explain how you push everything to the Liouville case. Okay? So we get the spectral resolution for the Liouville Hamiltonian. The QGFF. So this means that you can construct some eigenstates. They are indexed by P, real number P, Young diagrams, nu and nutil. So the Young diagrams are just these sequences of decreasing integers. And they encode the way this Virasoro algebra act on some, say, highest weight state. This one is just exponential IPEC. Okay? And then you have this creation operators, but in the Virasoro setup, acting on these guys. And so this Young diagram, they encode which generator you take to apply on this highest. So this family, it's a complete family of eigenstates for this QGFF Hamiltonian. And they give you also a spectral resolution. The difference now is that these states, they are not orthogonal. Okay? So you have Gram-Schmidt coefficients in your spectral resolution. You can compute them. It's not that much explicit, but still they have a definition. And they form what is called the Shapovalov form. It's just the Gram-Schmidt coefficients of this baby. Okay? So you have this spectral resolution. Okay. Anyway, for the QGFF, so everything is more or less explicit. And now back to Liouville. So Liouville is just that you have the free field Hamiltonian plus the potential. Okay? And so the potential is this guy here. The V, so it was this integral of the free field exponentiated free field on the circle. And so how do you construct the eigenstates for this Hamiltonian? So I stress that this, the approach we follow started with a paper by Jörg long time ago, using the, well, say the intertwining of the free field. So it's more or less the similar idea. So what you do is that, what is important in this potential is that here you have the zero mode in the we call that phi. It's C plus the sum of all other Fourier coefficients. So when you take the exponential here, you can single out the zero mode. Let me write this as C plus phi tilde, where this guy has no zero mode. And so it's an integral of phi tilde over the circle. Okay. So what happens is that when C is very negative, this guy disappears. Okay, so basically you expect to be able to construct the eigenstates for the Liouville potential Hamiltonian by prescribing the eigenfunctions to be close to the one of the QGFF when C is very negative, and then try to reconstruct the eigenstates for all other C's. Okay, so you can do this, so it's a purely analytic theorem. You can do this by using a Poisson operator. So actually, I'm changing a bit here because, let me write it this way. So the question is that you can construct eigenstates by imposing that when C is close to infinity, so L2 error term means basically, I don't want to quantify that much the error here, but it means that when C is very negative, this guy does not matter so much, right? Okay, so you prescribe the behavior close to minus infinity to be close to an eigenstate of the QGFF. Okay, plus an error. But the thing is that for the, well, this is called the scattering theory. So this is where Kola is an expert. But the thing is that, so you can, if you try to find an eigenstate having this behavior at minus infinity, you cannot do this, okay? There is some reflecting coefficient, let's call it S. So it's an operator acting on this free state. And we tell you that if you want to prescribe this asymptotic behavior when you are close to minus infinity, then you have to correct it a little bit with a linear operator. Okay? So this, you can see it as an operator acting on this state. You can correct this guy a little bit, and then up to an error, you have an eigenstate of the Liouville. Okay? So this scattering matrix here, it's the analytic theorem. If you just do a scattering theory, you will end up with something like this. But this guy here is not explicit at all. Okay? It's already quite a statement to claim that the scattering matrix is this operator here. Okay? So so in the beginning, you have this analytic theorem that tell you that you can construct this map. So you have a map between the free state and the Liouville state. And you can also show analytically that actually this map, in the parameter, complex parameter here, it can be analytically continued. Okay, so this can be done with purely analytic tools. And from this, what I want to explain now, but it does not give you any description of the eigenstates, okay? You need to compute them to prove formulas for this theory. And to compute them, we need to bridge again with probability theory and representation theory. Okay, but what will be very interesting is this, is the fact that we can continue the eigenstates holomorphically. Well, this is not a surprise. If you just look at the eigenstates of the Laplacian, they look like this. Okay, so for sure you can analytically continue them with this map, right? So here it's more general, but it's not a big surprise that there is analytic continuation. Okay, so now the trick is to play with probability theory to understand what are these eigenstates. And along the way, we'll see that the scattering matrix is given by this reflection coefficient, which has this form here. And also that the states, when analytic continued, they obey this reflection stuff, which is not the case in the free field. Okay, the states in the free field are different, but here up to this coefficient in the Liouville theory, the states at alpha and 2q minus alpha can be identified. Okay, so how do you do this? I will try to explain with Segal how you identify the eigenstates. Okay, so there is a geometric way of understanding the eigenstates. So let's take the amplitude of a disk with a marked point inside. So this amplitude, it has only one boundary. So it can be sort of as an element in the Hilbert space. Okay? Okay. So now recall that the propagator, the semi-group that we have of dilation, is given by the amplitude of the annuli. Okay? And what happens when you glue a disk inside an annuli? You still got a disk, right? So basically, this means that, so you can use Segal to see that the amplitude of a disk is an eigenstate of the Hamiltonian. Okay? Because you apply the propagator to this state. Segal tells you that you still got a disk, so up to the scale that can be dealt with the geometric rules I mentioned for the amplitude. The scale is this guy here. So it tells you that you've got an eigenstate for H with a disk. Okay? So at least it gives you some eigenstates, but it's not enough.
the disk amplitudes. Okay, what is the correspondence, the link between this disk amplitudes and this Liouville eigenstates? Recall that we have this family of eigenstates that we obtained analytically. They can be analytically continued in the parameter alpha, and when you continue alpha to the real region, so to the real line, okay, these eigenstates, they are given by the disk amplitudes. Okay, so the analytic continuation of the eigenstates, when you are what we call the probabilistic region, meaning that alpha is real and less than q, then you can show that the psi alpha and the disk amplitudes are the same. Okay? Okay, so in some way, we have a probabilistic representation of the eigenstates up to the fact that there is an analytic continuation in between. Okay? But here, the disk amplitudes, they don't give you all the eigenstates. It's not complete. So how do you create all the other eigenstates? So again, you play with the flow of deformation. So you take a holomorphic vector field, you look at the amplitude that you've got in the gray area, and you have again a semigroup like for the free field. And the thing is that this HV, it will give you the Virasoro operators, but in the Liouville setup. Okay? So you have this probabilistic representation. You can differentiate and find that this operator that you define with the flow of deformation, it's more or less the Hamiltonian of the Liouville theory plus some operators, Ln and L tilde n. And again, these operators, they give you another representation of two copies of the Virasoro algebra, so meaning all these relations here, with the same central charge as the QGFF, but they are not the same as the Virasoro generators of the free field, and the difference, the relation between the two is given here. Okay, you have an explicit expression. So Guillaume mentioned this relation in his talk, Jörg in a former paper, and the relation is that the Virasoro generators in the Liouville are the same as the QGFF up to this term here, which is again a Gaussian multiplicative chaos. Well, the point is that if you try, so I don't remember, but I think someone asked, how do you prove this commutation relation with this relation? Well, then good luck. Because, we tried, I don't know, okay, clearly there is no way to prove this commutation relation with this relation. Actually, we don't see, at least we don't see how to prove it. Okay, so it's an indirect way to.
There's a problem with domain, so you cannot compare.
Yeah, the domain are awful. So even heuristically, okay, let's forget about mass. Even heuristically, I don't see why this relation leads to.
For example, in the left-hand side, you say have something quadratic in mu, but on the right-hand side you don't.
Yeah,
these two guys should see it, right? Because otherwise it contradicts everything. I mean, just expand the left-hand side, right? It's in powers of mu. Then the left-hand side is quadratic in mu. The right-hand side is linear. Means that just the V commutes with B. How else it can be?
All this.
Yeah, just substitute this. You know that L naught satisfies. I mean, in zero order mu, I mean, the relation holds. Then we have to check it in the linear order mu and in quadratic. In the left-hand side. Quadratic and right hand side.
Yes, but okay, I'm not sure you end up.
Yeah, but like, I mean, the operators we have non-trivial.
Maybe you can show that it's the differential of some potential.
Maybe.
And then it becomes immediate.
Okay. Anyway, if it works,
it's tough.
But I don't. Okay. Anyway. Anyway, so what do you do with this Ln? So the same story as before. So we'll have this. Well, the picture is that we'll have this amplitude that we understand, and then we just make the Ln apply on this amplitude. So So again, you can construct. So we have these guys here, this family of new child, this psi here. They are given by our analytic theorem. Okay, we know that there are eigenstates with this eigenvalue here. So this is the length of the Young diagram. So you just sum the components. We know that these guys have a holomorphic continuation, and if you reach the probabilistic region, then you even have a probabilistic formula for these guys. When the Young diagrams are empty, so this is the primary states, if you want, in the Liouville setup. We also have probabilistic formulas in the probabilistic region for the descendants, but I don't write it on the blackboard. So just to give you a picture. And how do you create, how do you make the description of with the Young diagram? You just apply the lns we have just constructed on this primary state. So this is a way to encode probabilistically all the information you need in the eigenstate. Okay? And you can show that you have a spectral resolution for these guys, which is more or less the same flavor as for the GFF. So you expand like the Plancherel formula, but you have this Gram-Schmidt coefficients, which is again the Shapovalov form in the spectral resolution. So this means that we have a way to diagonalize the Hamiltonian with a family of eigenstates that is well fitted to the symmetry of our problem. Okay? So this is the first result, one of the crucial inputs we need to explain the bootstrap. Is that okay? Question? Okay, so now I'm trying to explain a little bit how you can prove the bootstrap with this probabilistic setup. So I need two inputs right now before the bootstrap. I will just explain a little bit the structure constants. So there will be a special role. So there have been many talks where structure constants were discussed, like the talk before. So here we are in the Liouville setup. So you look at the 3-point function on the Riemann sphere. So if you remember the geometric rule I mentioned, so here we have a metric, but the dependence on the metric is completely explicit by the Weil covariance. So you can choose your favorite metric on the Riemann sphere, like say the round one. And then also, because your correlation functions are Möbius invariant, or at least the dependence on the points x1, x2, and x3 is completely explicit. Okay? So you can choose your favorite 3 points on the Riemann sphere, and you focus on this quantity here. Okay, this is called the structure constant, basically. And you can compute it. I won't explain how, but there was something discussed in the talk before. There will be a talk for the Litvinov-Falayev formula by Baptiste. There's a proof in math now of your formula.
Finally.
Finally. Okay, so but you have this formula which is called the dose formula. You can compute this quantity. So I'm not sure I want to. So it will be completely useless in my talk. So you have this crazy formula. It is well, you can. It's holomorphic in all the parameters. There are some poles. It's a crazy function, but probably you know better than me. Some of you. But okay, what is important is that we can compute it. Okay, and there are the special functions involved.
Sorry, one hope of this explicit construction could be that you would be able to get it epsilon with this integral representation and so on directly, but it seems maybe you guys only got it from the same technique as Jörg did.
Okay, so the strategy you explain doesn't work in math, because the problem is not to find the shift relation. The problem, I would say, is the analyticity of the correlation function. Okay, because from scratch, you don't know that your correlation functions are analytic. And actually, the shift, you know the function, you know how to define it on a very small region, and the shift is way bigger. Okay, so
we did not proceed this way. The first step, the crucial step, is first to use the reflection coefficient to analytically continue, understand how the probabilistic expression extends analytically and so on. And then, okay, there is a proof. Okay, so the second input I need is some kind of, so I want to have a statement on for the conformal blocks. So we will have a way more described talk by Colin on Friday about the conformal blocks. I wanted to make it as simple as possible, so I used the plumbing coordinates on the space of Riemann surfaces. So basically how it works, so we fix the genus this time. We have this, we fix a Riemann surface, and we want to move a little bit in the space of Riemann surfaces. And one way to do this, so it gives you a system of local coordinates in the space of Riemann surfaces. So one way to do it is that you split your surface into a pair of points, and so this is one example. And then at the splitting curves, you insert an annuli. So this annuli, it has two parameters, so the length of the annuli and the eventual twist that for your annuli. Eventually, you can twist a little bit the annuli. So it's encoded, each annuli, it has this twist and this modulus, so it parameterized by a complex number. And you do this for every possible cut. So on my picture, you have a system of local coordinates from C3 into the space of Riemann surfaces by playing with these few parameters, right? Okay. So now the bootstrap, the conformal bootstrap tells you that if you look at the correlation function on a Riemann surface sigma q, so q means that we have an annuli parameterized by q plugged in the neighborhood of some given Riemann surfaces. The points here, so I remember Scott once asked about the points, so you let them fixed on this, so you take a point here, and it can be identified with a point here, so the points, they have a special position in the surface sigma q, so everything is well defined here. And the point is that this correlation function, they can be factorized. This is the holomorphic factorization. So here you have this row. It's an explicit product of DOZZ coefficients that I don't write not to saturate the blackboard, and some holomorphic series in the Q parameters that are the conformal blocks. Okay? So it's a bit of a sloppy statement in the sense that I don't tell you how you define globally the blocks and blah, 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 but Colin will do this this week. What I want to do now is just to explain how you get this formula, okay? And you will see along the way how you get this formula. I'm sure you can even write it yourself at the end. Okay, so to explain how, just one comment for physicists maybe. Of course, what will be important here is how you cut your surfaces into a pair of points, or what we call building blocks. But of course, there are many ways to decompose your surface into building blocks. And actually, the point is that all the way you can choose, they produce the same formula. Okay, this inequality is what you call a crossing symmetry. And for us, the crossing symmetry is completely obvious because this guy exists. Okay, so we show that it's equal to every possible decomposition, and so they are all equal to the same quantity. Okay, but if you start from this formula to define a CFT, check that the crossing symmetry is valid. Okay. But the probabilistic representation here helps a lot for the crossing symmetry. Okay. Okay, so the building blocks. So basically, the building blocks, there are three types, but they are more or less the same. It's just that you have the pair of points, of course, but you have also the annulus with one mark point and the disk with two mark points. But if you think of a given mark point on a manifold as the end of a point, then all of this is just the. So to have a point, you can. either have 3 boundaries or two boundaries and one other boundary which is just a mark point, and here for the same for the disk. Okay, so this is just a pair. They will be just used to decompose your surface into pairs. So just, and as I said, there are many ways. So for instance, you have a surface here with 2 points. Let me give you one decomposition into building blocks. So here you have a point, another one here, and then 2 annuli with 1 mark point. And of course, there are many ways to do this. You can have a disk with 2 points and a pair of points, or this one, where I just changed this curve here to this one, I think. Okay, so there are many ways, but you can apply the strategy to all these cuts, and you will end up with the same formula. Okay. What will be important is to so this let's say this building block, this pair of points, it's an amplitude, so it can be thought of as an element in H tensored 3 times. And what I want to do now is to evaluate this amplitude when I pair it to the eigenstate. This is an operator on H3, and I have 3 guys. I have a guy in H3. I want to compute this quantity, and so this is what I want to do now, and I want to explain it with Segal again, so with gluing. Okay, so how to compute that guy? Let me start with the simpler situation where I have no Young diagrams. Okay, so when I have no Young diagrams, remember that these eigenstates, they can be analytically continued. When I continue them to the real line, they correspond to disk amplitudes. Okay, and when I do the pairing by Segal, it's just gluing here, so those disks to the point. Okay. Okay, so if you make the analytic continuation, you end up where, in the case where the alpha j are real. And so by Segal, it tells you that computing this quantity amounts to computing what you have when you take this point, glue 3 disks at the end, okay, and try to compute. But if you glue 3 disks to a point, then you get a sphere, okay? And if you get a sphere, then this guy is just a structure constant. Okay, it's a DOS formula. Okay. So basically, this guy you can show, and it goes along this line, that evaluating the point amplitude to the highest weight state, it gives you the dose coefficient up to some metric dependent factor.
And this factor also depends on the lengths, like L1, L2, and
L3? The length of in the parameterization, so remember that the metric is of this form.
I mean, this overlap, should I expect it depends on this length?
The metric is nice at the boundary, if you remember.
No, I understand the metric, but...
yeah, but the metric tells you also that the length is 1.
2 pi.
2 pi, yes.
I see. But in the case of 4 functions, 4 boundaries, it will not depend on the length.
If you choose an amplitude,
yeah,
well, okay.
This one I understand. This is just a number, but the 4 point thing with the boundaries, it should depend on the, right? No, I just have it like in mind that, like in classical case, where those Mirzakhani formula, they depend on else.
No, but this is when you uniformize it with hyperbolic metric.
Yeah, but here is not.
Here there is no hyperbolic metric. We think just in terms of complex structure. We start with one complex structure, and you deform by gluing this flat annuli. You just cover a neighborhood of moduli space. But of course, you could uniformize using hyperbolic metric. Because the result does not really depend on. You can always choose a family.
Yeah, so the metric is such that each pair of pens has like unit length.
No. Yes, but the gluing is independent of the. So the pair of pens depends on the complex structure, but the gluing does not.
You can always, the dependence on the metric is totally explicit. You can always choose the metric so that it is nice enough at the boundary. And what you lose doing this, it's explicit. So, Okay, so, and you have the same story for, no, sorry. Okay, so now what happens when you plug some Young diagrams here, so it's way more complicated. But you can show that what you have to add here are some coefficients, that I call W here. These coefficients, I wrote delta. Delta means the conformal weights of all the guys that you've got here. And the three Young diagrams nu 1, nu 2, nu 3 that you've got here. Okay. And so to prove this relation, it's quite a job. Actually, you have to use the probabilistic representation of these guys, then translate it into identities that are the Ward identities, and then you see that applying this eigenstates here amounts to applying some partial differential operators on this guy. Then you compute what you've got here, and you end up with these quantities here. But it's computational.
But you know them in explicit form with W's. I mean,
yes, W's are explicit. Yes.
Closed expression.
It's a polynomial in the conformal weights.
I mean, in principle, I understand. I know how to compute it, but I mean, just general closed form expression for all the three arbitrary diagrams.
Yes, yes. You have an expression. I don't know if, but you know it.
No, I know them. One of them is empty.
Okay. No. You can. Yes, you can compute it. It's of course it's more messy, but you can have an expression for this guy.
I mean, the formal procedure is known to me, but I'm just, do you have like a closed form expression which you can plug in mathematics and just don't worry about it anymore because otherwise it.
I think.
I understand how to compute it using.
Well, there is no miracle here. I mean, in the end, we have a proof, but in the end, we get the description as you into the same numbers. So there is a closed formula. It's as close as you have. If you don't like it. No, but yes, you can compute them recursively using all the steps, you know.
Yes, and
it's a bit crazy.
You're saying that probability defines them uniquely, so these functions are known just directly to the computer. Yeah. And we don't, probably we don't.
Okay, so you have the same story. Sorry, yes, you have the same story. So for the disk with 2 points, because when you want to compute the amplitude of the disk with 2 points against an eigenstate, you apply the same strategy. So you are gluing a disk with 2 points with the disk amplitude with 1 mark point. You glue, you get a sphere with 3 points. So again, it's those coefficient. And when you again plug the descendants, then you still have this W, except that now you have only, in this case, you have only one nu. And in the case of the annulus, you have 2 nus, but this is the same story. For the annulus, you just glue 2 disks at the end of the annulus, and you get a sphere. Okay? So basically, all the building blocks, when you plug the eigenstate inside, you get those coefficients up to coefficients depending on the nu and nu tilde. What is important here is the factorization into W and W bar. Okay, so.
You say that all the eigen functions are represented by these disks with mark points? They're not, right?
All the eigen functions, yes, these guys.
Yeah,
they are disk amplitudes.
Are they all disk amplitudes, or?
They are all disk amplitudes, and when there are no Young diagrams. And for the descendants, you apply the lns, which have a probabilistic interpretation too. And the second information is that yes, we have a probabilistic expression as a disk amplitude, but with some further material inside for the descendants. It's like a stress insertion. And this stress insertion, their shape is important because they involve partial differential operators on the free field. And then using with the Wick rules, you can translate this stress insertions into PGE, playing with the Wick rules on the correlation function, and this is how you end up with the conformal Ward identities. And then you have to make some computation to get the W bar. Okay, so now let me explain how you end up with the bootstrap formula. So you start from a surface in your space of. So I took a simple case, genus to partition function. I want to compute the partition function of this surface. I choose a pair of band decomposition. Then I want to move a little bit in the space of relevant surface around this surface. So I insert my annuli in the cuts. And now, if you look at this surface, using Segal, you can see it as the gluing of this one and this one. Okay? So I have two amplitudes. One is attached to this one, and one is attached to this one. So by Segal gluing, you know that the partition function, it's the pairing of these two amplitudes, one attached to sigma 2, and one attached to this wall surface here. And again, Segal tells you that this amplitude on top, it's the composition of the amplitude on sigma 1, the orange one, and composed with the amplitude of the cylinders. Okay, but we have already seen, so the cylinder is just the semigroup, the propagator. Okay, so it's basically it's a Q1 edge. I only told you this story when Q is a real number, but can be extended to complex values. So this is just the propagator that you apply to the amplitude, and then you glue with you do the pairing with the amplitude below. Okay. Okay. So now what I will do is just a Plancherel formula. Okay. So I will insert, so in the Hilbert space, I will use the spectral resolution inside, well, like Fourier decomposition, if you like. Okay? So this is what I told you before, and then I insert the Plancherel formula. So it's starting to be a little bit messy. But here I just inserted the spectral resolution in between the two amplitudes here. Okay. So now, turns out that these guys, and I told you on top here, this is just the amplitude of sigma 1 that you compose with the propagator. It turns out that your spectral resolution is very well fitted to this setup because these guys are the eigenstates of the Hamiltonian. Okay, so the Qj edge applied to this quantity here, to the eigenstates, you know it very well. And let me, because yes, it was. So you need to compute it. Here you need two formulas. The first one is that Qj edge applied to Q plus IPJ. So I told you this morning that it is Qj to some power. There was the central charge divided by 12 plus 2 times delta J. And then there was the length of the Young diagram. Okay, so, but when it's complex, it's just Qj Uj, Qj bar Uj G. Okay? So this is the first, and then, sorry, times. So this is the first thing you need. And so you can get rid of the Qj this way. You insert this formula inside. This will give you the contribution here. And then you have removed these propagators and just compute the building block amplitudes that we just discussed. And so remember that, well, anyway, it's just the formula I gave you before. So once you have removed this guy, you need to compute, say, A sigma 1. Sorry. Okay. Then
you have to compute this on this side here, and the same quantity here. You use the formula I gave you. So this is, you plug these expressions here. So let me, yes, this one. So then you end up with this quantity to be inserted. You insert these quantities here, and you end up with a crazy formula. It's not crazy, but it's a bit. Yeah. Well, you end up with this factorization here when you plug everything I told you inside, and let me just write what you get for FP. So it's Fp of Q. So it depends on the spectral parameters P. The complex numbers Q that parameterize your surface, you end up with C of G. This is the metric dependent constant. Then you have all the contribution from these guys here. So you have times product 1, 2, 3. So I guess I have
surface.
P plus IPJ. Then I have a sum. 1, K2, K3. I guess I will have the sum over all Young diagrams with size Kj. Kj. I should have the W, mu W. So recall that this nu here is the collection of nu1, nu2, nu3, delta prime. Then I should have the Shapovalov. So I put you here. So Q.
But FP, you have no new tilde on.
There is no new tilde, no.
Ah, no, sorry. Okay, sorry.
Q. So there is the Shapovalov form. Nu J, nu prime J. Forgot something. You check.
Probably you forgot the Q.
The Q, yes, the Q.
To some power. Q to the power K1, K2 to.
And so these are the coefficients, and then there are Q1,
K1,
K1, Q2, K2, Q3, K3. Yes, this is your series. Okay. And this is how you get the conformal bootstrap, and you can do this for. Well, this is exactly the same strategy for any Riemann surfaces. You decompose it into building blocks. You insert the spectral resolution at the cuts, and then you use the computation of the building block amplitude, and you end up with some crazy expression, but yet this is the same expression as you guys get. So yes, but then the question is here, what kind of mathematical objects you can get out of these guys. So because here I gave you only local coordinates on the space of Riemann surfaces, and I told you that this function, they are holomorphic in the local coordinates, but then you may ask, how do you define these guys globally? This is what Colin will explain on Friday. Also, you may ask if this series converge. In our case, this is something we show, and the crux of the proof is Cauchy-Schwarz.
We show only for almost every P.
Yeah, but then it's almost every P. Basically,
so this is a conformal block on genus 2.
Yes. Yes.
Okay, and if you like for conformal block on genus 1, you can do also.
Yeah, you can do.
Okay, just make an example.
Also put up of this W's and I mean, you just draw this picture and immediately got this. Why did you know W?
Yeah, in genus 1, say you can do it together if you like. So you take this guy here. Then you choose your favorite cut. So let's say this one here. Well, this one is okay. So you have two. So this is just two building blocks, two underlined with one point. You insert the identity here and here, and then you reproduce the computations. Yes. So I think. Yeah. So one nice thing is here that yes, the convergence on the conformal blocks is just boils down to a Cauchy-Schwarz argument. It's just basically is the fact that you have, more or less it's a scalar product. Okay? And so you can always estimate these quantities here by using Cauchy-Schwarz by the quantities that you would get if you had the same amplitude on both sides. And then probabilistically this quantity is positive. So you have an integral that converges. This means that the integrand is converging almost surely in P. Okay, this is why you have a soft argument for the convergence of the blocks using probability.
In which region of, so what is the, so here you have a triple series in Q1, Q2, Q3.
So I think, as far as I remember, it's for modulus of Q less than 1.
Okay, so it's
is it correct, or I don't remember, it's less than 1, right?
Or 1 plus epsilon.
1 plus epsilon?
I mean, then you can still take another chart. And,
yeah, you can extend. In the end, you can extend holomorphically on Teichner space actually by covering many. But it's not a function. You have to think of it as section of bounders.
But in this form, this series, its modulus is 1, right?
More than 1 is 1 plus.
You think more than okay, so more than 1.
And just as a reminder, you said it, but so the conformal weights, was there some, were they complex parameter, or were you assuming that they were? I'm just trying to understand the convergence in which regions of all the parameters.
Alphas, you mean, of alpha?
Yeah, of the alphas.
That's exactly the question I wanted to ask also. So the two, if I remember, alphas was all smaller than Q.
Yeah.
Was the condition alpha, sum of alphas.
Alphas, the alphas has to
be
smaller than Q, yes.
No, there's also two conditions on the sum of them.
Okay, no, but okay, yes. This condition, okay, that's one nice thing to remember is that actually the pairings, when you want to insert the amplitude, the operator that you got, they need to be a little bit more than just L2, they have to be Hilbert-Schmidt. But anyway, all the amplitudes that you've got are not Hilbert-Schmidt. Okay, the weights, they have to be large enough. This means that the sum of the alpha j has to be bigger than Q times the probabilistic of your surface. This means that when you cut, you still have some constraints. Okay, the amplitude, they have to be.
I think it would work also for alpha complex in some region, as long as we can define the amplitude probabilistically, and it's in the Hilbert space. All this would work the same, I think. The problem is more like the Q plus IP, no?
No, I don't think so. You have a problem, I think, for the. No, even I think Zamruchikov says that there are some discrete terms appearing when the
yeah, of course, but it's for real alphas, which is fellow bounds, everything. And then you may try to continue just deforming the contour.
Yeah,
that's, I mean, it's clear that it's possible. This one might be very complicated.
When you want to, yes, so there is this region which is correct, and when you want to go beyond, you have to perform an initial continuation, and they are a bit subtle, so it's not completely clear how.
But we can extend to a bit alpha in the complex.
Yeah, of course.
The amplitude, yes, but then when you do it's when you do the pairing and you expand the spectral resolution that you don't know that the series converge.
As long as the element in the Hilbert space, we can do this.
As long the element, you mean the amplitude? Yes, but if this condition is not satisfied, then you're not in the Hilbert space, and then so you don't know that the blocks converge.
alpha to be imaginary, you need gamma to be less than 0 or 2. Gamma goes outside the range, right? For alpha imaginary?
Yes. And so the question
what is gamma?
Gamma or alpha?
Gamma.
Gamma, no, it's real.
Because alpha and gamma are related to each other through this Q.
Yes, this guy is.
Inequality.
Yeah.
But yes, but it's just an equality.
Yeah. So imaginary gamma means imaginary.
Gamma is fixed and it's real, and you cannot. Well, perhaps you can, but it's far from straightforward to continue this theory to any complex values. So it's stuck to the real line between 0 and 2. So what we do is this region here, and gamma is on this interval.
Chi, can you remind me what chi is?
Chi is Euler characteristic.
Does it? I mean, does the result imply some statement like the correlation function in these regions in normal or something like that?
You mean?
Do we get some? I don't know. From all these, do we get some information about how it of alpha and central charge?
All the questions related to the
all building blocks, you know the structure, right? But then you kind of
for gamma, you cannot continue in gamma. So the question may be on the alpha if you want.
Yeah, I mean.
And if you want to have the structure of the poles in alpha.
Yes.
Then, okay, it's not completely straightforward to extract from the bootstrap because if you know the poles of the block, then you don't know how it behaves under integration.
Yeah, I mean, in physics we have some like
if
arguments when we can predict some of the poles.
If I had to answer your questions, I would be more confident using the probabilistic representation. Then we see the poles, perhaps not all, but you can understand the first poles at least, and maybe you can iterate a bit.
I mean, speaking about analytical continuation, it would be nice to have like a good understanding of the poles, for example. If you know all the poles, I mean, that's a lot of information. Not all.
Yeah, but using probability, you can identify some poles.
Yeah.
And not necessarily trivial. But because the states, the psi alpha, they are analytic. But then, when you plug them into, when you evaluate them into the amplitude, then there are some bounds because of here, there are some bounds, and even though the states are analytic, then the correlation function may there may be some trouble inserting.
Yeah, I understand. The integrator might have some poles which pinch the contour. But.
And by the way, I would also mention that perhaps the guys from VOA are not familiar with this way of introducing the blocks. And Colin will explain on Friday how you can see the conformal blocks as operators acting on Verma modules and so on. Okay, so perhaps more what Jörg described in his papers. So this is not what I wanted to discuss today. I wanted to be more handy and see how it works probabilistically with Segal. Okay, and this is all I wanted to tell you. Thank you.
Thank you.